Chapter 12 Kinematics of Particles. Second, Curvilinear motion. Curvilinear motion, if a particle is moving along curved path. Position. Note: consider the motion of a particle along a curved path. It is represented by a position vector r bar. The line OP is called position vector. As the particle will move along the curved path, the value of r bar will go on changing. Velocity. Consider after a short interval of time delta t, particle has occupied new position p prime. Delta r bar is equal to change in position vector. Average velocity v is equals to delta r bar by delta t for very small interval of time. Delta t tends to 0. Instantaneous velocity at p is limit delta t tends to 0. Delta r bar by delta t. V is equal to dr by dt. During small interval of time delta t, the particle moves the distance delta s along the curve. Magnitude of velocity is called speed. Speed is equals to limit delta t tends to 0. Delta s by delta t is equal to ds by dt. Note: in curvilinear motion, velocity of particle is always tangent to the curved path at every instant. Acceleration at the direction of velocity is continuously changing instant to instant. In curvilinear motion, it is responsible to develop acceleration also at every instant. Consider the velocity of the particle at p to be v and at position p prime to be v prime. Average acceleration a is equals to delta v bar by delta t. For very small interval of time delta t tends to 0. Instantaneous acceleration at p is limit delta t tends to 0. Delta v bar by delta t. A is equals to dv by dt. Note: acceleration comes not because of the change in magnitude of velocity, it also comes because of change in direction of velocity. In rectilinear motion, displacement, velocity and acceleration are always directed along the path of particle, whereas in curvilinear motion it changes its direction instant to instant. Therefore, analysis of curvilinear motion is done by two methods: curvilinear motion by rectangular component system, curvilinear motion by tangential and normal component system. Rectangular component system: if a particle is moving along a curved path, its motion can be split into x, y and z direction as an independently performing rectilinear motion. Position vector r bar is equals to xi plus yj plus zk. Magnitude of position vector is equal to square root of x square plus y square plus z square. Velocity vector v bar is equals to dr bar by dt is equal to vxi plus vyj plus vzk. Magnitude of velocity is equal to square root vx square plus vy square plus vz square. Acceleration vector a is equals to dv bar by dt is equal to axi plus ayj plus azk. Magnitude of acceleration is equal to square root ax square plus ay square plus az square. Direction is given by the relation cos alpha is equals to x by r is equal to vx by v is equal to ax by a. Cos beta is equals to y by r is equals to vy by v is equals to ay by a. Cos gamma is equals to z by r is equals to vz by v is equals to az by a. In coplanar motion, we can consider particle is moving in xy plane. Position vector r bar is equals to xi plus yj. Magnitude is equals to square root x square plus y square. Direction is equals to tan theta r is equals to y by x. Velocity vector v bar is equals to vxi plus vyj. Magnitude is equals to square root vx square plus vy square. Direction is equals to tan theta v is equals to vy by vx. Acceleration vector a bar is equals to axi plus ayj. Magnitude is equals to square root ax square plus ay square. Direction is equals to tan theta a is equals to ay by ax. Derivation of rectangular component of velocity. As the direction of the velocity of a particle is changing continuously in curvilinear motion, so it is convenient to deal with its components vx and vy. Resolve delta r into two rectangular components. Delta r is equals to pq bar plus qp prime bar. V is equals to limit delta t tends to 0. Delta r by delta t is equals to limit delta t tends to 0 pq bar by delta t plus limit delta t tends to 0 qp prime bar by delta t. V is equals to limit delta t tends to 0 delta x by delta t plus limit delta t tends to 0 delta y by delta t. v is equals to dx by dt plus dy by dt. V is equals to vx plus vy. Magnitude of velocity is equals to square root vx square plus vy square. Direction is equals to tan theta, which is equals to vy by vx. Derivation of rectangular component of acceleration, resolving delta v into two component delta vx and delta vy. Delta v is equals to q r bar is equals to q s bar plus s r bar. A is equals to limit delta t tends to 0 delta v by delta t, which is equals to limit delta t tends to 0 q s bar by delta t plus limit delta t tends to 0 s r bar by delta t. A is equals to limit delta t tends to 0 delta vy by delta t plus limit delta t tends to 0 delta vx by delta t. A is equals to dy by dt plus dvx by dt. A is equals to ay plus ax. Magnitude of acceleration is equals to square root ax square plus ay square. Direction is equals to tan phi, which is equals to ay by ax. Note: in tangential and normal component, we are not considering any reference system. We are interested in velocity and acceleration of that particle or body along that trajectory. For example, roller coaster ride, train on curved path, car rider on curved path trajectory. Tangential and normal component system. Velocity vector v is always directed in the tangential direction. However, the net acceleration of the particle at a particular instant need not be along the tangential direction. Let the particle has a velocity v at a time t and velocity v prime at a later time t plus delta t. Resolve करो delta v को into two components delta vt and delta vn. Delta v is equals to q r bar is equals to q s bar plus s r bar. Delta v is equals to delta vn plus delta vt. For acceleration, we have a is equals to limit delta t tends to 0 delta v by delta t, which is equals to limit delta t tends to 0 delta vt by delta t plus limit delta t tends to 0 delta vn by delta t. A is equals to dvt by dt plus dvn by dt. A is equals to at plus an. Magnitude of acceleration is equals to a is equals to square root at square plus an square. Direction is given by tan theta is equals to an by at. Note: when delta t is very small, it tends to 0. P prime coincides with the point P, and direction of at and an coincides with the direction of tangent and normal to the path. Rho, component of tangential acceleration at. S r bar represents the change in the magnitude of velocity v. Therefore, at is equals to limit delta t tends to 0 v prime minus v by delta t is equals to limit delta t tends to 0 delta v by delta t. At is given by dv by dt. Thus, component of tangential acceleration at is equal to the rate of change of the speed of the particle. Component of normal acceleration qs bar represents rate of change of direction of the velocity. Qs is approximately equals to v d theta for a small change in angle theta. Delta vn is approximately equals to v delta theta. An is equals to limit delta t tends to 0 v delta theta by delta t. If rho is the radius of curvature of the curve, then we have delta f is equals to rho d theta. Delta theta is equals to delta s by rho, delta s being the length of the arc pp dash. An is equals to limit delta t tends to 0 v delta theta by